Hello, good morning. Welcome to this World Large River and Delta System Source to Sink online talk series. So this is basically the second webinar, but it's a kind of official invited talks. Last Wednesday, I gave an opening and introduction and a big picture introduction about the fluxes and the feet of the World Large River derived water and sediment to the sea. Today, we invite Professor Jim Best from University of Illinois at Urbana-Champaign, UIUC. He was talk about the nature and the pace of anthropogenically-induced change within the world's large rivers. Before I hand over to him, so let's introduce again how to attend this live presentation, because this is our second webinar. I would like to see this information again. First of all, the time we set at this time, the US East Coast summertime, 9 a.m. There will be the afternoon in London and Paris. And in the evening in Beijing, 10 p.m. in Tokyo, and I'm sorry to our Australia colleague, it's 11 p.m. But this is kind of the best time window we can accommodate most of the colleague and student from all over the world. So of course, you can access this meeting, have the interaction through the Zoom meeting room. As I mentioned the last time, my Zoom account has limitation, only allows 300 participants. So if you are out of mainland China, if you are able to, you also can watch this live presentation through the YouTube channel. So as I put it here, called tinyurl.com source to sink. So currently there's around 28 people watching on the YouTube now. And at the same time, if this Zoom meeting could be full, and for the colleague and the student in China, if this is full, or if you're able to, you also can join this meeting through the Tencent meeting or the Vivo meeting. So the meeting ID is this one. And so, okay, before I introduce Professor Jim Best, I would like to mention that our next week talk is Dr. Liz Chamberlain. So from Vanderbilt University, she will talk about the dating method, what she used from her study in the Mississippi River Delta and Ganges-Brahmaputra Delta. So same time, same way to connect it. And the last week presentation and today's presentation will also be available on our YouTube channel. So if you go to the YouTube channel, you will see, will be archived there. So today's talk may be available this evening after 12 hours, but you always can come back to review the previous talk. Hope we can build a good study series. Okay, so our today's talk, invited speaker, Professor James Leonard Best. He is the professor from University of Illinois at Urbana-Champaign, and I think he's kind of crossed a different department geology, geography, and GIS information science. James graduated from University of London, and after that, I believe he worked some years in University of Leeds, and then in 2006, 14 years ago, he came to United States, UIUC, as a professor. And James is world-known, top-notch in the river geomorphology and sediment dynamics study. As you can see from this website, he's also teaching a course called Big Rivers of the World. This matches exactly our talk series, the topic. And one thing I want to let you pay attention, he also have a very productive professor and with a very high citation. If you look at today's Google Scholar citation, his citation is up to 14,000, more than 14,000. That's really something. And so I think I have already said enough. Now it's time to pass to Professor Jim Best. Jim, you can share your screen.
Okay, thanks. Thanks, Paul. Many thanks, Paul. I hope you can see the full screen now. And I should say right at the beginning, many thanks indeed for the invitation to present the talk. And I know you said last week the conditions under which this came about, so my commiserations that you had to cancel sabbatical plans. But looking at the range of talks that you've got coming in the next few months, looks a fantastic lineup, and it's really a fantastic use of your time. Thanks very much for arranging this. It'll be fascinating to see what's coming up in the next few months, and also be able to use that as both a research and a teaching resource. So my thanks to you for arranging all this. And I must say, actually, looking at that list of talks that are coming up, I must admit, I feel a little bit like the warm-up act really for the rest of the series, in that what Paul asked me to do today was to present just an overview talk on anthropogenic change within the world's large rivers. And I should say right at the beginning that over the last 20 or 30 years, I've been just phenomenally lucky to be able to work with a whole range of people on a number of rivers across the world, from some early work with Phil Ashworth out on the Brahmaputra after the disastrous 87 and 88 floods, through to work on the Paraná with Oscar Orfeo, Mario Amsler and Dan Parsons, and then on to recent work and ongoing work on the Amazon with Renato Almeida, Marco Iniberto, Andrew Nicholas, all those people and many more, some of whom I'll mention in the talk, have really been fantastic to work with, and also enabled me to think and work on a range of rivers. And I'm hoping to reflect some of that today. So many thanks to those. And also, this is going to be a review talk, and so I'm going to reference quite a lot of papers in the literature, and I've tried to put all of those references in the talk and the journals that they're from. But many thanks to all those people, some of them I know who are tuned in today to this, and some of the work that I'm going to try and cover in the next 45 to 50 minutes. So we're all used to looking at these sorts of aspects of rivers. This is from the Upper Amazon, looking at SRTM image of the Amazon, and you can see there a whole range of terraces, beautiful chunks out of those terraces with past positions of the main Amazon River, and also superimposed dendritic networks on the exposed terraces. So we're all used to thinking about the geomorphology and the geological context of big rivers and the sediment that they feed to the world's great deltas. But also, of course, big rivers are really at our roots. And we've only got to look back through to some of the early civilizations, through from the Nile Valley, through across to the Fertile Crescent, across the Harappan Valley civilization in the Indus River, across to the Yellow River. Those early civilizations, of course, intimately relied upon the context and the nature of big rivers, and enable a whole range of advances in both agriculture, infrastructure, and the way that human society has developed. Of course, involving transport. And if we look at some of the earliest world maps, this is the 1520 map of Pietro Coppa, we can see, of course, there just the dominant role that rivers had, both in allowing us to navigate and locate on land masses, and of course also providing a route whereby explorers could reach into the continental landmass. So rivers and big rivers have always been at our root. And of course they still are, and we still utilize and use big rivers for a whole range of purposes, some of which I'll try and touch on in the next 45 minutes. Transport and industry being one of those. This is a barge on the Mississippi River. And of course, rivers provide a whole series of services, through from hydropower, through to recreation, through to abundant fish resources, source of protein for millions of people across the world. And More than that, of course, rivers, examples here, mainly from the Amazon, contain an incredible abundance and diversity of life. So the ecology of big rivers as well is intimately connected with the evolution, the geomorphology and the geological evolution of those river basins, and the ecology and the diversity of ecology that has thrived and existed in these big river basins. But of course, when we think about the stresses that are being caused to the world's big rivers at the moment, one of the main drivers to this is the world's population. And we can look at population growth. We can see on the right-hand side here the curve for both the growth rate and the total world population. We see that in 2019, we passed about 7.7 billion. And we can also see that we're going through the demographic transition here, where we're going through from increasing down now to decreasing rates of birth. And this still means, though, but by 2050 and then by 2100, there's still going to be several billion extra humans on the face of the earth. And so that is, of course, creating a whole range of stresses, some of which are manifested in the big rivers of the world. Right at the core of this is also thinking about a whole range of things such as the UN Sustainable Development Goals. And water is explicitly named in two of these, both in number 6 and number 14. But I think water and rivers run the thread throughout all of these goals. And there are a whole range that intimately rely upon rivers and water, through from reducing poverty and hunger, right through to, of course, supporting life on land, and right through to peace, justice, and strong institutions and governance. So water and big rivers really runs a thread throughout these whole range of sustainable development goals that are key in our aims for 2030 and beyond. What I'm going to do today is look at a range of stresses on the world's big rivers. And one thing I just want to say is I'm not going to mention anything about groundwater, but we haven't got to forget groundwater and, of course, its intimate role and connection with what we're going to be considering in terms of water and sediment flux in rivers. And this is a paper from last year looking at some of the environmental flow limits to global groundwater and when that limit is going to be reached. And so all I'm saying today has to be placed in the context also of groundwater resources and their use and their limitations. So right at the beginning, some of the inspiration for the review that I took a couple of years ago for this was from Edgardo Latrabesse and group's work on damming the rivers of the Amazon basin. I think it's a beautiful paper, a very influential paper, published in 2017 in Nature, where Edgardo and colleagues looked at damming of the Amazon basin and looked at a whole range of measures by which we could look at the effects of this, and importantly brought in, I think, a geomorphological context into looking at present damming and what potential future effects could be. And this paper really inspired me to look at a whole range of rivers, and the upshot of that was a review paper in Nature Geoscience in 2019, and I'm going to base most of what I say today on that, but try and update it in parts. And I think also another really very influential report for me was that produced by the United Nations Environmental Programme through this report on transboundary river basins, transboundary water assessment program, that looked at a whole range of river basins and a whole range of stresses that were acting upon those basins. So I'm going to draw on these today, and I'm also going to draw on a whole range of other papers that were intimately involved in what I attempted to do in this Nature Geo review paper. So the stresses on the world's big rivers, let's list them at first. Well, a whole range, of course, from climate change through to damming, whole range of pollutants coming into the world's big rivers, how we withdraw and transfer water across rivers, the introduction of non-native species, how that can begin to then fragment the river ecosystem, and how that also may be exacerbated by issues such as sediment mining. And of course, the tricky one may be right at the end, the role of governance, the collaboration between civil society groups and government institutions. That government and how we manage river basins has often been called the wicked problem because of the difficulties of getting a whole range of different actors together in order to achieve river basin management. What I'm going to try and do today is look at just some of these. I'm not going to be able to cover them all, but I'm going to look at some aspects of some of these and some recent work that has been done on each. And that's what I'll try and cover in the next 35 minutes. So first, let's look at climate change and flooding. And the map that I want to begin with is this one here. And this is taken from a paper in 2016 by Arnell and Gosling. And this is just one image from their paper. And this shows the consistency in the magnitude of the estimated 100-year floods in 2050 from 21 climate models. So they've taken 21 climate models, looked at the magnitude of the 100-year flood and seen what that would be like in 2050, showing regions where we'd get an increase and a decrease in the magnitude of that 100-year flood. And we can see, of course, from those range of models, that there's a very mixed picture across the globe. So we can see, for instance, such as areas in the southwest United States and up into the Volga and across into parts of the Ob. We can see there that there's most of these models, over 67%, show that there's going to be a decrease in the 100-year flood magnitude. We can look at a whole range of other rivers, the Congo, the Lena and the Ob, Russia's great Arctic rivers up here, through to a whole range of rivers then down in Southeast Asia, right across from the Huanghe, right through to the Ganges and the Indus, again showing an increase. And there are rivers, and I think the Nile in some ways it typifies this, where the pattern, especially in the lower Nile, is very uncertain, which makes estimation of water resource issues into the next 50 or 60 years problematical, and we'll come back to that later. But what this is all showing us, and hydrologists have been saying this for years, is that stationarity in our flood forecast is really gone. And we're having to look at a very changing scenario across the globe, and the water and, importantly, the sediment flux that's coming down the world's big rivers. If we go in and take a little bit more nuanced view on that and water shortage, and we look, for instance, just at Asia's water towers, and this is from a paper by Imazil and Berkins in 2012, this is looking at different facets of future water shortage. So you can see the abbreviations for these on the right-hand side, through from glacier melt, right down through future precipitation, through to economic development and population growth. These are showing the different areas of where there might be future water shortage issues. And what this diagram here is, on each of these little shapes here, looks at the importance of each of those. And all I'm going to do is point out that when we look at the difference across the rivers of Asia, we can see for things like the Indus that things like how glacial melt is going to become is going to be changed in the next 20, 30 years is going to be really important. Whereas if we go across to the eastern side here, that degree of glacial melt becomes less important in its influence on water resources, and their future precipitation trends become important. So when we begin to look at the causes for and the facets of different water shortage, future water shortage, then there are a whole range of different factors that are playing into these rivers across Asia and playing in differentially across that space. One indication of this complexity is given by some work that was led by Steve Darby at the University of Southampton and a whole range of collaborators a few years ago. And this was looking at the Mekong River. And what this study did was to look at historical records of both flow and then try and pass out from that the contribution to that flow that was provided by tropical cyclones. And so what we got here is a whole series of hydrographs, the total in here in grey, and then the contribution to flow from tropical cyclones underneath. By then looking at relationships between discharge and sediment flux for suspended sediment, what we're able to do then was to then hindcast both estimates of suspended sediment yield in total, but also then try and separate out and pass out the suspended load that was attributed to the tropical cyclones. And the upshot of that is that approximately a third, about a third of the suspended sediment reaching the Mekong Delta from those historical records looks like it was associated with tropical cyclone related rainfall. And then what the paper went on to do is to say, well, if we can do that, let's look into the records that we can access from the 80s onwards and look at that temporal change. And that then shows a decrease in sediment load from the 80s through to the present day. And you can see that on the right-hand graph. And if we then do the same game of then separating out the cyclone-induced contribution to that sediment load, the figure we get out again is about 60% of this sediment load decline is due to a shift in the climatology of the tropical cyclones, essentially due to a shift in the path of the tropical cyclones over the last 20, 30 years. So in terms of identifying changes due to different aspects of climate change, there's many complexities here. And for looking at the influence of tropical cyclones, which we can see from this map here of cyclone track, is of course vital in this part of the world, that we have to also factor in that when we're looking at both changing hydrology, but also changing sediment flux. And as we'll see in a moment, the Mekong in particular is subject to a whole range of stressors, not only from climate change, but from a whole range of anthropogenic stressors, including damming, that we'll come on to in a moment. Just to produce a contrast to that, when we look to Russia's great rivers, and here the Lena River, the forecasts there are really all indicating increases in flow, and some work done quite a few years ago, maybe a decade or so ago, of course, indicates that increase in discharge, which may be between 18 and up to 70% by the end of the century, that's going to increase sediment flux. And sediment flux might increase by 30 to 100% in rivers such as the Lena. And this graph in the bottom right, which plots stream power against grain size, basically it's making the point here that with some of these increases in sediment load and discharge that may come in some of Russia's great Arctic rivers, some of those may be potentially liable to perhaps a change in planform if they cross any thresholds that we can establish. So the rivers of the Arctic, again, and with melting permafrost, changing very greatly due to climate change. Damming, of course, has been an issue that has raised much debate over the last 20, 30 years with the advent of the great growth in mega damming across the world, through from dams such as this one here, the Juru Dam on the Madeira River. Two big dams recently been finished and closed on the Madeira, through to huge dams like that on the Three Gorges on the Yangtze. And of course, we know from a whole range of work the ecological change that can be induced by such dams. So the Landsat images on the top left are from the Xingu River in the Amazon, looking at the morphological change brought about by the construction of the Belamonte Dam. And you can see the differences that it's made to both the active channel and the flooding of the reservoir there. And of course, there are a whole range of different environmental impacts above and below dams. And the diagram on the right here is from a summary paper by Forsberg in 2017, alluding to some of the upstream effects within the reservoir. So things such as potentially increased greenhouse gas emissions from rotting vegetation, as well as mercury contamination and mobilization, through to the downstream effects, things such as decreasing sediment supply, the sort of hungry water that Matt Condolf talked about many years ago, through to a whole range of factors such as decreasing nutrient supply and changes to both the flood pulse and potentially the fish yield in the downstream channels. So a whole series of change brought about by large-scale damming. But of course, it's worth remembering that hydropower forms a significant percentage of the renewable resources, energy resources that we generate as humans at the moment. So it's a key debate between the ecological effects of hydropower and, in different countries, the need for hydropower for social and economic growth. A case in mind, again, going back to the Mekong, is a beautiful work by Matt Condolf's group, some of which he has reported in 2014, looking at a whole range of scenarios for dam build out in the Mekong. So on the left, we've got definite dams, and this is showing the percentage of sediment trapping, 50% estimated from these. If we go to the right-hand side, with then full build out in the tributaries, you can see that increases to about nearly 70%. In the middle, where we've got both full build out of planned dams in the tributary valleys as well as on the main stem, what this study indicates is if all of those were in place, then perhaps up to 96% sediment is trapped in these reservoirs. So of course the implications for then sediment reaching the delta are enormous. So hydropower and damming and the issues around that, and we'll come back to this right at the end, have obviously got a very turbulent time ahead in the next few decades. Let's turn to pollution now. Pollution of a whole range of sources, and I should say I'm showing quite a few images here from just wonderful photography of Edward Bertinsky today. And you can see on this river a whole range of different pollutant sources and oils on the water surface. We can also think about a whole range of other pollutants. So if we look at religious festivals like the Kumbh Mela on the banks of the Ganges, a festival held every 3 years. This is a 2013 event that attracted about 120 million people to the banks of the Ganges over a period of a couple of months. And of course, the demand of that temporary population on the river is huge. And so some studies, this is one by Tyaga et al., look at a whole range of stresses there caused by the people at the Kumbh Mela upon the Ganges. So the top left is showing just biological, chemical, oxygen demand and total suspended solids. You can see all of which go up with population, as does turbidity in the bottom left, as does, of course, the fecal indicators from coliform bacteria with population. You can see there both for fecal and total coliform bacteria there on the bottom right. You can see those increasing with the number of people, but then also, of course, exceeding the thresholds for standard and safe bathing. So huge demands and placed on a river system by a huge influx, temporary influx of people. And the Ganges faces many issues, not only from industry, not only from inputs from both industry and domestic use. And that, of course, is raised a whole series of legal issues. And there's a fascinating case a few years ago when just for a few months, the Ganges and Yamuna were granted the same legal rights as human beings. This was prompted by some legislation that originated in New Zealand, but that was then overturned by the Indian Supreme Court a few years later. But this issue of the interaction between pollution and society and law and government is one that's going to come back to many rivers, many big rivers in the next few decades. The Transboundary Water Assessment Programme in 2016, one of the maps that they produced, and there's a whole range in that report, looked at both nutrients, largely from phosphates and nitrates, and wastewater, and looked at different categories of risk from very low through to very high. So all I'm going to point out here is some of these. So for instance, we can see from nutrients, we can see actually across here in the Mississippi, the real importance at the moment of agricultural runoff of nitrates and phosphates that's feeding down to large problems of hypoxia in the Gulf of Mexico. We can see within the Ganges and the Brahmaputra, many rivers here down in Southeast Asia, again, the problems that will be created by nutrient overloading, which when we also then combine that with wastewater, and we can see those problems both extending through a whole range of rivers here, down through into Congo, the Nile, Zambezi, and then also into rivers across in South America. You can see there are many issues in large-scale pollution and what we can do with that. Now, this was in 2016, this map and this assessment was made, and that was really before we began to realize the impact of plastics and micro and macro plastics in pollution in the world's rivers. There's some fascinating work being conducted in the last few years, and some fascinating work still continuing to come out, looking at the size and the distribution and the loading of microplastics and macroplastics within the world's large rivers. And we can see here both the sources of plastic waste in the grey colours on the world map, as well as from this study by Lebreton et al. In 2017, looking at the inputs from the rivers. And this study showed the inputs from a whole series of rivers, but stressed the role of some of the large rivers of the world in providing some of the largest inputs through to ocean waste. I know that's been revisited in studies of smaller rivers now, but the world's large rivers, of course, carry a good amount of material, plastic material, that gets into the world's oceans. Again, the other pollutant as well, that there's been some fascinating work just in the last year or two, is looking at the world's large rivers and the content of antibiotics that are put in both from industry, from agriculture, and also from our waste, human waste. And this is causing potentially some issues that will become more serious. And this is one of the first studies that I'd come across, a really nice piece of work looking at some of the main rivers in Shenzhen in China. I'm not going to go through this, but you know, the conclusion here was that the antibiotics introduced into these water systems were promoting the proliferation of antibiotic resistant bacteria. And so the corollary, the end result of that, is that the antibiotics that we have will become less effective, less efficient in treating certain clinical cases. And I think there's another form of pollution that's coming both from agricultural land and from domestic waste and sewage that is very rightly receiving a lot of attention at the moment. Now, in these COVID-19 times, that's caused a change to so many lifestyles across the world. I think it's also interesting at the moment to look at some of the fascinating work that's coming out from looking at wastewater and looking at the content of the COVID-19 virus in sewage as a way of early detection. And so there's been some really encouraging work looking at detecting the virus within the sewage system as a way of looking at community transmission and spread without having to do individual testing, which can then be targeted perhaps later. And you can see in the bottom right there, the lifespan of the virus, you know, within solid feces can be 3, 4, maybe even more in terms of days. So the COVID pandemic is also causing issues that we as river scientists and big river scientists need to be aware of. And of course, that goes for not just the direct detection, but it goes across into issues of governance, politics, and society. So, you know, one example of this, of how the virus is affecting what's happening in terms of the world's river pollution is at the moment in the United States. So with COVID, and WOTUS is the Waters of the United States, it was legislation that looks at the essentially controlling pollution and a whole range of other things in America's waterways, and POTUS, and POTUS is the President of the United States. I know some of my colleagues have suggested a different adjective might be more appropriate for the P actually at the moment for the present incumbent. But what has happened in the last few months is that the administration has used this to lessen up how strict the legislation is for people and industry, and especially industry and agriculture, polluting the US waterways. And the pressure on this is, or the reasoning for this is that if pollution in the waterways is necessary in order to encourage economic growth because of the pandemic, then that should be allowed. And as water scientists and as inhabitants of these big river valleys, this is a really detrimental step in beginning to control issues, for instance, such as the hypoxia in the Gulf of Mexico. Non-native species, let's move on again. I'm not going to say very much about this, but the introduction of non-native species across the world into river systems has been a real issue in many river basins. And one example of this is the Wabash River, which is a tributary. It eventually comes into the Mississippi. It runs down along the border between Illinois and Indiana here in the States, in Illinois, my home state. And this is an image of carp, a whole range of so-called Asian carp here that were introduced into the Mississippi system in the 1970s, but escaped into the main rivers and now have been spreading through the system. And there's a huge effort at the moment trying to stop the spread of these into the Great Lakes. They're incredible animals. They outcompete nearly everything else, and they can breed into huge numbers very quickly and outcompete everything else. So the introduction, accidental or on purpose, of these different non-native species is changing ecosystems in many river basins across the world. An indication of the effect of that over a longer period of time was given by a study by Leuven et al. In 2009, who looked at the River Rhine. And so this diagram here on the left-hand side is just looking at the connections of the Rhine with a whole series of different rivers. So we go from the Ems through to the Neman, which is going here across this way. Here's the Volga, and then connecting through to the Black Sea, the Mediterranean. And what it's showing basically between these rivers is the date of connections, canals between these rivers. And so if we think about that, then if we look at the catchment area essentially that could potentially drain or connect to the Rhine, that's gone up through time as these connections have been made. What they were also able to do was to look at the number of non-native species that were introduced. And of course, it's no surprise that that number of non-native species is going up through time, but also it's going up as the number of connections are increased through the river basin. And of course, there's a whole range of different vectors there. So some of those species are introduced through ship traffic, some are introduced accidentally, some are introduced by ballast water. And the indications for some of these is like one species was able to propagate from the upstream right down through to the mouth of the Rhine in between 12 and 18 months. So the pace of change, the spread of these non-native species can be very rapid. One issue that has begun to receive a lot of attention in the last few years is the issue of sediment mining, both sand and gravel in the world's large rivers. And of course, the demand for sand is increasing as population grows, as urbanization grows, as construction grows, as our need for sand for both silicon chips right through to gravel and sand for a land infill and concrete has soared over the last few decades. So sand and gravel are vital for us for building materials, for employment, and that's especially the case with small-scale artisanal sand mining and economic growth. And the amount of sand that we're extracting and the value of sand has gone up through time. But of course, with that need for sand are some of the detrimental effects. And I'm just going to play a little part of a beautiful short documentary directed by Kalyani Mam, a Cambodian filmmaker, looking at different aspects of sand mining. Actually, this is on the estuaries and the mangrove areas in Cambodia. Some of the effects that we begin to see from sand mining include things such as channel incision, which then link through to bank instability, potentially the loss of floodplains by mining on the floodplains, as well as infilling of the floodplains, increased turbidity in the water column during sediment mining, which can begin to alter the habitats, and the damage that can be caused to infrastructure by a whole range of those factors of incision instability. And in some areas of the world, people have linked sand mining to crime, both locally and nationally, and violence and a whole range of gender issues. So whilst we rely upon sand inherently for many developments, sand mining, if it's poorly regulated or unregulated, can cause huge issues. And one place where we see the need for and use of sand mining has been in Singapore. So here's Singapore in 1973. And if we look at now an image of 2018, the land area has increased by about 20% in 40 years. So if we just flick between those of you who have flown into Singapore airport, you can see it there on the eastern side. You can see just the massive land growth in Singapore over the last 40 years. Of course, we've got to say, well, where does that sand come from? Well, yes, it comes from, in part, Cambodia. And if we look at the trade statistics over the period 2007 to 2017, Singapore reports that it imported about 74 million tons of sand from Cambodia, from both the coast and rivers. If we look at the same period, the amount of sand that Cambodia says that it exported was only 4% of that. So part of this relies upon the detection of the sources and the trade of sand, and looking at the issues of both legal and illegal sand mining. So the situation for sand and gravel mining is really so dire in some rivers that it's hard to see in some rivers the ecosystem being able to recover. And what I'm going to do now is highlight some work on the Mekong River as an example of the magnitude of these issues. And this is some work that was spearheaded by Chris Hackney and Steve Darby. The whole group was involved in this. And what we were been doing over the last few years is looking at estimation or trying to estimate the sediment flux through the Mekong and looking at channel change. So this is part of a much bigger project. But as part of this, what we've been able to do is to develop methods to look at the transport of both sediment in both suspension and as bed load. And we've done this through a range of different stations in Cambodia on the lower Mekong, through from Karachi, through down here. We've actually gone south of Phnom Penh, but the data for this paper are generated in these sites here between Karachi and Phnom Penh. What we've done is estimated bedload transport by repeat multi-beam echo sounder surveys. So we're doing that essentially to look at sand dune migration and then using that translation to calculate volumetrics. We've used acoustic Doppler profilers to look at the backscatter intensity and calibrate with suspended sediment concentration. And through that, that calibration from field surveys over a period of 3 years, and then using those calibrations for estimating past sediment flux, we've been able to try and estimate the amount of sediment moving down the Mekong and contrast that with the amount being extracted. Before I move on, it'd be remiss of me not just to highlight actually another piece of work that's recently come out this year, headed by Julius Cisneros here at Illinois, looking at dunes in large rivers. And just to point out that when we look at dunes in the world's large rivers, when we look at their lee side angle, the lee side angle for all these rivers, and there's a whole range here on the histograms from the Amazon right down to the Paraná. If we look at lee side angle, look at percentage, you can see the blue line there is really giving the value about 10 degrees. You can see many of the dunes, or the vast majority of dunes in the world's big rivers, are much lower angle than we thought before. And the relationships between dune height and water depth, here they are for these different rivers from the Amazon right down through the Mekong, the Missouri and the Vaal in the Netherlands. We can see the relationship between flow dune height and flow depth. We often think about that being a value of about 0.3 of the flow depth. Well, we can see again the vast majority of dunes are much smaller than that in their relative height. And we can see also lee side angle is low, not only in deep rivers, but also in these shallower rivers. There's also another beautiful piece of work that's recently just come out by Suleiman Nashband and Ton Hoytink. Experimental work, but also looking at the bed load, mixed load and suspended load dominated flume experiments. And again, seeing how as we go from bed load through to suspended load, that the slip face angle reduces. So most robust work is really suggesting that the causes for these low angle dunes are, there's a range here, but suspended sediment flux is important. That might feed through to turbulence modulation when we get high sediment yields, high suspended sediment yields, and bedform superimposition, and also hysteresis, non-uniform flow effects may be really key in producing lee side angles that are lower than we think traditionally. That's important for when we begin to estimate things such as flow resistance and flood heights. So let me move on. So what we did was to quantify bed load transport on the Mekong. And so the value that we get out of that when we do calibrations of bed load transport against stream power, we look at the percentage bed load versus suspended load with stream power, and we hindcast that backwards through time. We get an amount of about 6 million tons per year. If we then look at estimates for the extraction of sediment from the Mekong, and we're relying upon a whole range of work here, but the value that we're going to use as a central estimate is about 50 million tonnes a year. And the take-home message, which you can see at the bottom, is the extraction of sand now in the Mekong is about 8 times more than the natural supply. So it's unsustainable. And the effect of that is not only that that's contributing to delta-wide incision of up to a couple centimeters a year, which is causing big issues in terms of things such as the intrusion of the saline wedge into the channels and the concomitant effects that has on agriculture. This multi-beam map here in the lower left is showing some of the sand mining pits that are in the Mekong just near Phnom Penh. It's also potentially having an impact on riverbank stability. And this is some work that's also reported in the paper, some simple analysis of riverbank stability. And so what this is indicating is that if we begin to do things like lower the riverbed by 6 meters due to local sand mining near the riverbanks, this of course can make the riverbanks become unstable. The vegetated banks, which are often lower angle, tend to be more stable. But it's showing us that with unvegetated banks, if we lower the riverbed, by 3 meters, we can increase the instability of those markedly. And why is that important? Well, it's important because, obviously humans live on the riverbanks. So this beautiful LiDAR scanning animation Julian Leyland produced here shows the abundance of dwellings, agriculture on the riverbanks. And so that riverbank erosion and its effect on infrastructure, of course, is vital. When we think about the sediment flux going down to the Mekong Delta, then of course this again is vital for us to consider in terms of the effect upon agriculture. And there have been several other papers I just highlight here that have looked at these effects. So a paper by Jordan et al. Found local lowering by up to 17 meters and highlighted the intrusion of the salt wedge. Some very recent work by Edward Park and colleagues also looked at not only riverbed mining, but also dike construction, and that's impact on flood frequency. And the last one by Barretti, right at the bottom there, begins to look at the implications for food production on the Mekong River Delta. So what can we do about this? Well, it's a paper from last year headed by Mette Bendiksen, looking at maybe establishing an agenda for sand, looking at how we can begin to identify sustainable sources, look at alternatives to sand, how we need to increase our reuse of building waste, how smart design can begin to lessen our demand for sand. And the three at the bottom are the key ones maybe for us to consider today, is the role of governance, education, and monitoring. And as field scientists and modelers, then obviously that monitoring and modeling is key to us. And if we think about how we are going to place this into the broader context, then when we take this agenda for sand here, this sand gem, we have to place this in the context of our field measurements and how we do that increasingly from remote sensing and then hopefully citizen science, and then bring that into a modeling approach that then feeds back into how we develop policy and how we set our societal goals to allow sustainable extraction. And as I said there, one of the great hopes is the changes we have in measurement techniques for both looking at things such as quantifying sediment flux in terms of suspended and bedload sediment, as well as increasing use of remote sensing from drone and satellite imagery to look at a whole range of river processes, from estimation of river discharge through to estimations of sediment mining. And Chris Hackney is leading some really beautiful work at the moment looking at using satellite imagery to look at the footprints of sand mining. So can we differentiate footprints like this and footprints like this from above water mining, and then also thinking about sediment plumes from barges and dredge boats to look at the footprints of underwater sand mining to allow us to begin to look at the location and the intensity of sand mining more holistically across big rivers. All of this ties into, of course, sediment flux and the effects that a whole range of anthropogenic stresses have on sediment flux. I'll just highlight two papers here in passing. One recent paper by Xinyin Wu and colleagues looking at anthropogenic change on the Chinese rivers. I'm not going to go through this in detail, but it's a beautiful study that begins to look at a whole range of factors such as reservoir trapping, water resource and its utilization, and conservation issues. And the text I've highlighted in yellow there just points out the relative importance of those. And you can see their estimation is 45% of that decrease in sediment load has been due to reservoir trapping, with water resources, i.e. diversions, and water soil conservation, and the incredible change that's occurred within, especially the Yellow River, the Huanghe, over the last few decades on sediment flux and how they've affected sediment flux. The other paper, again, I just want to highlight in passing, is this recent one by Li et al., which again looks at sediment flux, but looks across a global picture. And whilst it finds that many rivers are dominated by stationary trends, when we look at the world's large rivers, a quarter of it experienced changes in water flux in the last few decades, 40% experiencing changes in sediment flux. And over the last decade, their estimate is that 21% have decreased in sediment flux, and 13% of that decrease is generated by Asian rivers. Lastly, let me move on to the issue of governance. So the interaction between civil society groups and government institutions. I'm not going to say much about this, mainly because it's such a complex issue. And as I said before, it's often been termed a wicked problem. But I think one area just to highlight the issues of governance are in the Nile at the moment. And 2019 was the year of the Nile Basin. And the Nile is changing greatly at the moment in its potential hydrology and sediment flux. And that issue revolves around governance. And before I come back onto the Nile, this is another stress map that's produced by the Transboard Boundary Water Assessment Programme, looking at governance across the globe. And so we can see here a whole range of river basins, and these are these broad categories from high risk from governance right through to low. And we can see, some rivers down here that certainly had issues potentially in their assessment, through to those in the Congo, even through to those up here in the Yukon, the ones you can think of at first. But you can see here, that the Nile is graded as moderate. This is back in 2016. But of course, in the news in the last few months, last few years, the great issue in the Nile at the moment is the construction and now the filling of the Grand Ethiopian Renaissance Dam. And this is changing the political structure as well as the water balance potentially within the Nile River Basin. And there's been a lot of literature, a lot of debate on this, and a lot of negotiations between Ethiopia, Sudan, North and South Sudan, and Egypt. And this is ongoing. So these ones here, this was from the 3rd of August when these talks resumed. Egypt withdrew from the talks on the 5th of August, and now South Africa's urging Ethiopia, Egypt, and Sudan to continue these talks. And the talks here are obviously about the rate of filling of the reservoir and the control of the water that comes through to the lower Nile. So I know Paul last week said one of his ambitions was to take his chirp profiler and profile the new Nile Delta in Lake Nasser above the High Aswan Dam. I think when Paul celebrates his 100th birthday, his research group can maybe take him out to do some sub-bottom profiling again, but he'll need to be moving his sub-bottom profiler potentially up to the Grand Ethiopian Renaissance Dam, where the new Nile Delta will have formed. And very finally, let me come on to the pace of change. This is from a paper Steve Darby and I published just a few months ago, looking at a review to set the pace of change for a whole range of stresses in some sort of context. So this diagram on the right shows a whole range of stressors, some of which I've discussed today, some which I haven't. And what it's doing is showing the time scale in these colors here. This is from short time scale through to long time scale, and some of the effects of these stressors. And you can see here, we're stressing that all of these have to be seen through the lens of governance and economic, societal, and political shocks. And we can think again of current COVID crisis and pandemic as an exemplar for that. And if we're thinking schematically about stress and resilience through time, we can think about a whole range of background resilience, and we can think about climate change providing a very important and strong but rather slow increase in stress. On top of that, we might superimpose increases in flood frequency and magnitude, but then we can also think about a decrease in resilience produced by other non-climate related stressors, such as damming or potentially pollution in certain areas. So this is a simple view from simple additive stressors, but what it's highlighting is that we have to consider the time scale as well as the nature of multiple stresses in order to know how our river system and our large river basin resilience is going to be affected. I think perhaps I've been affected too much by thinking about the pandemic, but this is a really interesting paper by Alasegi and colleagues in 2017, just highlighting how maybe we can learn from medical science in how we view river basins. And I think it's interesting to reflect on the role of medical staff and all those involved in the last 6 months, and just how much we rely upon them in everything that we do. We're very lucky in what we do as careers compared to many people who are working in a whole range of fields that are far more risky than ours. But their key is that we need to diagnose, treat, and then prevent. That's what we need to do in order to assess how river basins should be managed. I think the thing I want to add to that is that we need to triage. We need to be able to prioritize what that patient care, what that river basin care is. And to do that, in order for us to triage, we have to assess and realize and monitor and measure not only the range of multiple stresses that affect river systems and large river basins, but also their rate, their pace of change. And my last slide is the Mekong River as an exemplar for this. And this again is from a paper that Steve and I published, highlighting that a whole range of other beautiful studies have fed into this, but how we got to then, of course, look at sea level rise, but how substance, and this is some of Philip Mindehill's group's work, beautiful work on substance, how we have to look at substance, how we have to look at changing sediment flux, both from damming, as we see dams throughout the Mekong, and we also look at sediment mining. How we also have to consider both climate change and its nuances from things such as changing tropical cyclone path, and how all of those then begin to link on to other things such as arsenic pollution, which is an issue throughout many Southeast Asian deltas, and is also linked to issues of subsidence and changing relative sediment flux. So what we need to do as river scientists is to be able to monitor and measure and look at these multiple stresses in large rivers. And I think that has to be our goal. Many thanks for listening. Now, I'm really happy to take any questions.
So Jim, this is fantastic talk. And so we have a two-way to ask questions. If you click the participants, then you can raise a hand if you want to talk directly to Jim. Or I already seen some, our guest already posted a question on the chat. Jim, you also can click the chat. So I can read a couple questions to you. And if you like directly ask, you can go to participant and raise a hand. So that's the first question here. And so let's see. Oh, here's a good question from Haris Gupta. And he said the sediment mining and the damming are two processes control the downstream export of sediment. Jim, have you seen that question on the chat? If we ignore downstream impact or ecological impact. And so his question is, because the sediment trapped behind the dam in the reservoir. So he said, do you think it will be wise if we can devise some ways to trap the sediment, go to the reservoir and use them for construction activities? Basically, he said sand mining behind the dam reservoir instead on the delta. That could be solved both problems. So what's your comments on this?
Yeah, no. Thanks for the question. I think that's a really important issue. I think there are many things involved in that. I think yes, in terms of looking at the sediment going into the reservoirs, that is essentially when it goes into the reservoir and it's deposited, you've got several things you can do. You can either try and flush that downstream, and I know many reservoir large dam management strategies have sediment flushing strategies to try and move sediment out of the reservoir to increase its lifetime, but also to increase sediment flux downstream. So that's one way. The other way, of course, as you highlight, is that potentially is a source of sediment that you could actually take out and use as construction material or whatever. That means that you don't have to then dredge that and mine that in the lower river. So I think, as you point out in your question, you've got to ignore the impacts of the downstream ecological change. But yes, I agree that there are ways of potentially using that sediment to look for construction in the trapped sediment within reservoirs, as well as to either trying to do that or flush sediment downstream. The challenges that you face in that are of course many, both from the mechanics of doing that, through from how you have flushing strategies, and that relates through to actually how much water you have in the reservoir to enable you to flush, as well, of course, of the pure economics of how you may take that sediment from the source region through to the market, and that will vary widely across different countries.
Mm-hmm. Actually, I think this question and the proposed solution is very smart. But do you know any river system people sand mining behind a dam or reservoir for construction?
Sorry, Paul, was the question, do I know any areas where they're taking out the sediment from the reservoir for construction? On large rivers, no, I don't. But again, I mean, people who are listening in maybe have more idea on that than I.
Okay, so the second question from Professor Li Dongfeng. He said, thank you for a great talk. Could you talk more about the bed load, the significance of measuring bed load for big river? He questioned, is there any new progress or technologies to quantify the bed load flux and associated uncertainty? So, do you know, even bed load is not a big contribution for the total sediment flux, but still it's a big challenge for us to quantify the bed load. So yeah. What's your understanding?
Yeah, again, thanks for the question. I think you're right, Paul. I mean, if we look at, say, the estimation of the percentage bed load contributing to sediment transport in the world's big rivers, I mean, it's often a low percentage, just a few percent. Having said that, of course, that the effect on the riverbed and the construction of bars and islands, and then what that does to river mobility and bank erosion is much larger than that small percentage would suggest. So quantifying the amount of bed load transport in the world's big rivers has always been a massive issue for us. Mm-hmm. I think in the last few years, I think when we start to look at, say, direct sampling and all the range of things that we used to do, that is just so phenomenally difficult to do, and also so hugely wrapped up in many errors. I think some of the acoustic methods, and one of which I highlighted today in terms of looking at bed form tracking and looking at both the bed load tracking through dune translation, but also we can begin to do things like look at sediment in suspension and partial suspension from the acoustic backscatter. And whilst those techniques have issues in them in terms of acoustic response and the how site specific they may be, to me they offer actually a huge advantage in that we can begin to look at estimates of sediment transport over larger areas. We can look at the spatial changes in sediment transport potentially more easily. And as multi-beam systems become more available and cheaper and more deployable on smaller vessels, I think that being able to conduct that sort of analysis would be more and more important. So I think that sort of acoustic technology is important. And I think the other one that I just mentioned that also may become more important in some shallower rivers in the next few years is just the use of LiDAR that can penetrate the water column, as well as other methods, optical methods for looking at water depth. And again, although this may not be suitable for things like dunes, it may be suitable for measuring the translation of features such as sediment bars. And some of the work that I know we've done on smaller rivers shows that if we look at the accumulation of dunes and how they contribute to bar migration, if we measure the bar migration, that can give us, again, a really good estimate of the total bedload transport. So I think both those acoustic as well as those remote sensing techniques offer lots of possibilities where we can actually increase our measurement of bedload. But just to stress is that the measurement of bedload is, as well as suspended flux, is still really key for us to be able to do as a community across many of the world's large rivers, so that we've got a robust database through which we can assess the nature of any change produced by all of these anthropogenic stresses.
Okay, wonderful. So the next question is from KK Reddy. I don't know, she or her or he. So what's your comment on the impact of natural and human on small mountainous river compared to the large river system? Because today, Jim, you talk about most of the large river system. How about the human or natural impact to those small mountainous river system?
Yeah, again, thanks. Great question. And I must admit, my focus has been on large rivers and especially the large downstream floodplains. But I think those small mountainous rivers, of course, are subject to some of the same stresses. So I suppose we could look at, I don't know, for instance, what I highlighted in terms of glacial melt and the differential effect that that's having across the water towers of Asia. We've got to think, of course, those rivers and starting from glacial sources in the uplands, those stresses, of course, are very similar. But we can also think about issues of land use change. So if we think about things such as deforestation and we think about how that may potentially change sediment flux, then some of those stresses can be equally applied through to small mountainous rivers as well as large rivers. When we come downstream, of course, we're thinking about, I've highlighted some of the large hydropower today, but if we look at maps across, say, the States, or we look at maps across China, we've not only got a whole range of large hydropower schemes, we've got hundreds of thousands of smaller dams and check dams that affect both hydrology, sediment flux, and organic carbon. I'm not really touched on organic carbon today, but the flux of those are all affected by those smaller check damming schemes. So in response to the question, some of these stresses I think can be applied equally, but maybe in a slightly different nature to those smaller mountainous rivers that, of course, are connecting down to what I've been talking today in the downstream large river.
Wonderful. So Professor Xu Yijun from Louisiana State University, he asked, is there any recent work that documents the quantitative role of the bed load? So is there any new recent work, to quantitatively define the bed load in the delta,
It was a question, so I'm struggling to find the question here. Was the question basically the percentage of bed load versus suspended load? Was that the question, Paul?
I guess so, because that's the traditional, somebody assumption 10% or something. Yeah. But any recent new study or new understanding for us to get an estimate?
Yeah, I think there is, and selfishly, I'll point to some of the work that I've been involved in. But I think as we're able to quantify bed load and suspended flux better, we're getting to better estimates of that. So I think some of the work that Steve Darby has headed at looking at the Mekong, where what we tried to do is to look at suspended sediment flux from acoustic properties. We've been measuring bed load through dune tracking. And what we tried to do is hindcast that so that we can look at that changing flux through time, and also use both of those to get an estimation of the percentage of bed load versus suspended load. And I think there are several other groups that have been doing this in other rivers, from the Mississippi through to the Paraná, through to potentially the Amazon as well. And I think the values we're getting out are small. They're between 2 and 6 or 7%.
Oh, very good. So I think in the coming talk, Professor Mead Allison also talk about the sand transport to the sea. So now we have another question, Delson, and so please go ahead.
Hi, Professor Paul Liu. Hi, Professor Jim. Nice talk.
Thank you very
Here's
much.
Wilson. I'm from the University of São Paulo in Brazil. And my question is, would you expect impacts that are exclusively related to the sieving effect in terms of grain size caused by sand mining or damming? Because here in Brazil, we have this kind of effect that is related to the increase in runoff and deforestation that increases the sediment discharge. But also we have damming that would like sieve the grain size and maybe alters the average grain size and in the river at all.
Yeah. Okay. Yeah. Thanks so much. And that's a great question. So the question is that basically what you've got are the competing issues of deforestation that's increasing sediment flux, but potentially the reservoirs are then acting as a filter, which presumably are, without flushing, you're accumulating the coarser sediment within the reservoir and flushing the finer sediment downstream. Is that the question?
Yes. Yes.
Yeah.
Exactly.
Absolutely. No, I think you're absolutely right on that, and I think the answer to that is yes. I think you're right, and that will certainly occur, and there will be a filtering of the sediment size that's released downstream. The thing to add to that, before I just come back to the grain size, is of course when you look below hydropower reservoirs, you've also got the local sources of sediment that are being yielded by erosion of the river banks. And the sediment that is there. So I know, some of the work on the Mississippi, looking at, say, the effects of upstream damming on the Missouri, when you look at the flux coming down, the flux is less. But of course, there's remobilization of sediment in the lower Mississippi that's adding to that sediment load. So I think, we've got to consider what's being remobilized below and downstream the hydropower scheme. But you're absolutely right, is that the dams and the reservoirs are also providing a spatial filter. That is meaning that the flux of sediment that's going downstream is going to be more dominated by the finer sediment, and we see that, for instance, in the Nile from the construction of the High Aswan Dam in the 60s and 70s. And so I think you're right there, and part of the issue there then relies upon, if you need to change that, is there any flushing strategy that is appropriate? But of course, in large reservoirs, getting that coarser sediment from the proximal end to the distal end to flush becomes maybe potentially impossible. And then the issue then is, as the first question alluded to, is there any way then you could potentially use that coarser sediment that's trapped in the reservoir for construction purposes, rather than actually dredge out in the lower part of the river? So that's a great question. And I don't think, and again, other people correct me on that, I don't think that's really been incorporated into a lot of modeling yet. But that would be a fascinating thing to be able to do, to look at the longer term evolution of the channel downstream of some of these very large hydropower schemes.
That's wonderful.
Thank you.
Thanks for your question from Sao Paulo.
Actually, this is one of the purpose of this talk series. We want to stimulate all the kind of future study, particularly for the young generation. So let's see if any other question. I saw one person, Noah Lane, raised the hand. Do you want to ask? Do you want to speak and ask a question? If not, so James, I want to ask a question, maybe a last question, if no other question. You mentioned the Mekong, as also I talked about last time. The scenario, the reality is now is there's less sediment coming down. Then the sediment was taken away from the delta. Basically, the Mekong is kind of a negative export of the sediment to the sea. This is why the delta every year is kind of 20 meters retreat of shoreline. Do you know any other rivers, large river system, have a similar embarrassing situation? Like I don't know, like Indus or any other river, based on your understandings?
In terms of what the big reduction in sediment supply, well, I suppose the obvious one would be to point to the Huanghe and just the reduction of sediment supply coming down there, and actually what that did to recession of the Huanghe Delta. Yeah. So in terms of dramatic effect and change in load progression, that would be the one. I think also if you look at the effects of that, then the other one I would point to at the moment is in the Brahmaputra Ganges system and the Garai River. So if you look at the Garai and also what the flux of fresh water is going down the Garai, that was changed greatly. A whole different range of reasons, potentially linked to upstream water diversion. But what that has meant is that the saline flux now coming up the Garai into some parts of the Sundarbans is much greater than it was before, which is, of course, like the Mekong, has caused a huge stress on the type of agriculture. So I think, you know, the Hwang Hae, and I would say the Ganges Brahmaputra in its western part also shows some of those combined effects of the stressors of changing the hydrology. And you then have got, of course, the compounding effects of both subsidence and sea level rise, which is also changing salinity and actually what the saltwater intrusion and the distance of saltwater intrusion is.
Very good. So Professor Xu Jing from RSU, he has a question. Maybe this is the last question. If no other question, raise the hand. Okay.
That's fine.
Okay. Thank you very much, Jane, for the great talk. And also thank you, Paul, for organizing this wonderful presentation series. I wanted to come back to my initial question about the bed node, to the role of bed node in building delta, because we recently, from our work on the bed node in the Atchafalaya River, we realized that the bed node actually may have played a huge role in the progression of the delta. So my question is, if you are aware of any recent work that basically traces bed node, what is roughly the percentage of bed node in building an active delta? You know, so we know bed node has a relatively small percentage in the total sediment transport from a river. However, that quantity may be very much more important than the total sediment, because sand, the fraction, plays a huge role in the nearshore geomorphology. So I was just wondering if you are aware of any recent work that document the quantitative role of bed node on delta building. So, like I say, even so, sediment bed node makes up only 3% of the total suspended sediment. However, it may contribute to 40 or even 50% of the nearshore delta building. Yeah. Are you aware of any recent work?
Okay, yeah, thanks for the question. I'm racking my brain to think if I can think of any recent work on that. I can't think of it in the moment. I think, you know, it's a fascinating point you raised, and I, you know, as I tried to say, is I think bed load, when you look at the effects, say, upstream in terms of formation of, you know, islands and bars and the effects on morphology, bed load is key. I think the other, you know, thing that's fascinating to me in terms of that flux of sand coming down to the delta and its importance is not only the role of sand that's transported as bed load, but also the role of sand that's supported in temporary suspension. So, you know, when we look at our estimates of, say, sand flux in the Mekong, we've got bed load, but we've also got a lot of sand that's contributed by suspension. So I think the other thing that is even more difficult to pass out there is not just the role of sand that's transported strictly as bed load, but in high flow events, how much of that sand is all actually arising through temporary suspension. My answer is I can't think of anything at the moment that actually has looked at and estimated that percentage of bed load versus everything else in delta progradation. So I don't have an answer, but I think for me, and I can come back to you, you know, is the suspension, is the sand in suspension also a contributor? It must be to delta growth.
Yeah.
Yeah. Okay. So you know, I think, you know, there's potentially a huge role for that suspended sand, especially in high flow events, as well as that's strictly bed load. That wasn't a very good answer to your question.
That's fine. That's fine. Thank you. Thank you.
Thanks for the question.
Okay. Thank you, Professor Jim Best. And today on this Zoom meeting, we up to 95 participants. And in the other platform, Tencent, we have 155. And on the YouTube, we are up to 50. So it's roughly more than 300 participants. But as I mentioned, all the presentation you put in last week, this week, and next week we are already recorded, on the YouTube channel. So if you missed a part of the presentation, or if you want to go back to rewatch it, and we were including the caption, and if understanding the British English, so it's all there.
Thank you, Paul. And I say, if people have other questions or things that they would like to raise, please just email me or contact me on Twitter, and I'd be more than happy to answer. And I think you're right. This great thing about this forum, hopefully it can make more contacts across different countries across this whole range of subject areas. So thank you very much, Paul.
And the last thing, if you yourself, you want to contribute a talk, to the audience, or if you want your advisor or colleague, they can give a very good talk like Jim's just did. And please send me a recommendation. We're happy to make arrange to host, add to this talk series. Okay, if no, I'll see you next Wednesday, same time. Okay.